Okay, so today we're going to talk about universal gravitation. So let's take a look. Let's start off by taking a look at this PhET simulation. So if we look at these two guys, let's pretend, or girls, these figures, they're holding on to masses. If we were to increase the mass of one, let's take a look at what happens to their force vector on one another. So this arrow right here represents the force of M1, force on M1 from M2, and this force vector represents the force on M2 from M1. So if we were to, actually let's keep the masses the same, let's just drag them closer to each other. We'll notice as we drag them closer to each other, they both increase in the same amount of force of gravity. So they have the same amount of force acting on each other, but in opposite directions. Okay, now let's see what happens if we increase the mass of just one of them. So if we increase the 200 kilogram mass to, let's say, 600, how did it affect both of the masses? It has the same effect on both masses. Even though we increased the mass of just M1, it still had the same impact on M2. So this force on M2, this vector right here, got just as large as the force on M1 by M2, except the opposite direction. If we decrease the radius, it changes at the same rate. So we can notice some relationships here between the masses, the radius, and their effect on the force of gravity. So as the mass increases, let's see again, as the mass increases, the force increases. This is a direct relationship. Either mass, so if we increase this mass, the force increases again. So we know that it's dependent on both mass 1 and mass 2, force of gravity is. So somehow we're going to have a relationship with M1 and M2. And we know M1 and M2, if they increase, force of gravity increases. So M1 and M2 must be in the numerator of our equation. And as we increase the distance between them, we decrease the distance between them, we're increasing the force of gravity. So this is an inverse relationship. As we make R smaller, the distance between them, R, smaller, F increases. So somehow R must be in the denominator of our equation. So gravity is an attractive force between any two masses. These two masses could be the force of gravity between you and the earth. It could be the force between you and the person sitting next to you. It could even be the force between you and your calculator sitting in front of you. Any two masses. Here's our relationship. Like we said earlier, M1 and M2, as they increase, Fg would increase. If R were to increase, since it's in the denominator, if R were to decrease, so if we move the objects closer to each other, Fg would increase. So M is the mass of each object, R is the distance between their objects, and we always want to remember R is the distance between their center of masses, so the center of their object. G is the gravitational constant. It's equal to 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. So here let's look at it again. If we have M1 and M2, they both impart a force on each other, force of gravity. If we were to take these same masses and move them closer to each other, their force increases. If we were to increase the mass of 1 compared to our initial trial, we'll notice that the force increases when we increase the mass of M1, keeping M2 constant. But they increase the same, even though we kept M2 the same. Okay, so let's take a look at an example. So let's say there's a calculator sitting on your desk in front of you. We want to find the gravitational force between you and the calculator. Let's say you have a mass of 140 pounds and your calculator has a mass of 300 grams. And it's a distance of 50 centimeters from you. Let's find the gravitational force that exists between you. Often, this is called the universal law of gravitation. Newton's universal law of gravitation. So there's a couple things we need. The distance between you and the calculator. So we're assuming we're talking about the distance between our center of masses, 50 centimeters. The mass of the calculator, which is 300 grams. And the mass of you, which you need to convert to kilograms. We want to divide by 2.2. We know for every 1 kilogram is equal to 2.2 pounds. So if we take our equation, F sub g equals g m1 m2 over r squared. Well, g, even though it's out here in the front of the entire equation, that just means it's in the numerator. So 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. Multiplied by our first mass 1, the calculator, 0.3 kilograms. And the mass of you, 63.6 kilograms. Divided by the distance between us, or between you and the calculator, which is 0.5 meters, and we want to square that. If we take a look at our units, we'll notice that if we have kilograms times a kilograms, that's kilograms squared, that cancels. And then we have a meters squared in the denominator, with a meters squared up here in the numerator, that cancels. So we're left with newtons, which is exactly what we want for a force. So that's where the units were derived for our gravitational constant. You get an answer of 5.09 times 10 to the negative 9. Okay, let's go ahead and look at one more simulation, this time not between two random objects, but between our sun and our Earth. So if we take a look, here's our sun, here's the Earth, and luckily we can kind of change the distance between these, and we can move them around wherever we want. So the moon is also in this figure. Let's take the moon out of the picture for just a moment. So if we take our Earth and we were to move it closer to our sun, we'll notice that even though the sun is much more massive than the Earth, both of these objects feel the force of gravity imparted on them from the other object. The same force, but opposite direction. If we bring our moon in here, you may be able to see the very small blue vector on it. It feels a force of gravity. It's kind of torn, actually. If you look at it between the sun and the Earth, it feels some force from the Earth and it feels some force from the sun. But it feels a larger force from the sun than the Earth. Even though it's closer to the Earth, it feels a larger force to the sun right here in this particular setting because of its comparison in mass sizes. The sun is much more massive than the Earth, even though the distance is further. So if we were to do an actual perspective of this, let's say we're over here, we'll notice that our moon is always pointing, the force of gravity is always pointing toward the Earth. It's never pointing toward the sun. And it's actually in orbit around our Earth. And this is why, because it's captured by the force of gravity of our Earth. Okay, I think you guys get a good idea.